Students, let us now try to address few important questions which you might come across during your exam. So that is one of the main reason why I picked this topic up again after your exam, because now you will have a better conceptual understanding. So picking up the questions, what is Fermi energy of conduction in electrons? Because conduction electrons are the fermions, okay, like protons and neutrons. So if we try to calculate EF, we have taken this as U, so UF, the Fermi energy for conduction electrons, okay. So UF for, we are trying to calculate now UF for conduction. To calculate okay, UF for conduction electrons, okay. So if we try to calculate UF for conduction electrons, what is UF? The Fermi energy. So the Fermi energy for conduction electrons we are trying to calculate and also we would like to address the question whether this Fermi energy, this is number one, and number two is whether UF depend upon the size or volume of the conductor, whether UF depend upon the size and volume of the conductor. Size and volume of the conductor, okay. So you see so we are trying to calculate EF for conduction electron at T equal to 0 Kelvin. This is our constraint. We are not going to do it for higher temperature, because at higher temperature the cutoff is not very sharp. You cannot say that above the Fermi energy there are no electrons if you go for higher temperature, because you have seen in the graph that that graph which we drew last day, that the cutoff is very sharp, isn't it, for Fermi energy. If you remember the graph that we had drawn, I'm trying to address the question why at T equal to 0. If you remember, Nu by Gu, the occupation index, we had plotted against U last day, where we showed that at T equal to 0 the cutoff is sharp. This is UF. That means this corresponds to T equal to 0. That means above UF you have no fermions, and below UF it is fully filled. Whereas at higher temperature what happens, it crosses like this and you have some fermions above 0. So above UF. So above the Fermi energy at T greater than 0 you have fermions. But at equal to 0 the cutoff is sharp. So calculation becomes very easy over here. So we consider T equal to 0. Okay. So this diagram is very important to explain Fermi energy. So do practice this for your exam. Alright. So basically then what can you say? That the number of electron is equal to the total number of energy states occupied by the electrons from 0 to UF. Because each energy state can have only one electron, isn't it? So if you have, say, if I draw the energy levels like this, okay. So if I keep on drawing the energy levels like that, say this is 0, this is 0, energy value 0 at 0 Kelvin. At T equal to 0 Kelvin, this is energy level 0. Then you have U1, U2, U3, and like that it goes on, U4. So it goes on like that up to say UF. So up to UF states you have one electron in each level, because it satisfies Pauli's exclusion principle. No two particles can occupy two quantum states. Okay, so one electron in one level up to UF. Above UF, no electrons. So you can say number of electron is equal to number of levels, isn't it? That's what that concept we are going to utilize in our calculations. What is it that we will be doing over here? We will say that the number of electron n is actually equal to integration from 0 to UF, okay, the number of cells between 0 to UF, isn't it? So finding the number of electrons at T equal to 0 Kelvin is quite easy, because you can just simply integrate from 0 to UF, and if you put down the value of the expression that we had written down previously, you will see this is nothing but equal to 8 root 2 pi v by h cube. If you just do the integration, this is the constant, m to the power 3 by 2 integration 0 to UF, okay, u to the power half du, okay. And this, if you do it, it's a very simple integration. You can show that this is equal to, well, 16 root 2 pi v, okay, m to the power 3 by 2 by 3 h cube, okay, UF to the power 3 by 2. Alright, now that is actually equal to n, the number of electrons within your Fermi energy level. Okay, so you can simply write, you can just take UF over here straight away. UF, the Fermi energy, you can find the value of the Fermi energy. It is equal to, you try it out yourself, it's pretty easy. Okay, 8 square by twice m 3n by 8 pi v whole to the power 2 by 3. So this actually addresses the important question, that does Fermi energy depend upon the size and volume of the conductor? No. You see, the Fermi energy UF depends upon number of electrons per unit volume. So that is the important conclusion that we draw from here, that the Fermi energy UF depends upon n by v, that is the number of electrons, that is the number of electrons per unit volume. This is also known as electron concentration. Okay, so let's stop over here to do two more important calculations, so that, but before we stop, let us address one important question. What is the question? Important question. Well, do electrons have zero energy at 0 Kelvin? Question. Do electrons have zero energy at 0 Kelvin? Okay, if not, why? Well, electrons at 0 Kelvin do not have zero energy. The energy of a system of n electrons, we'll show just now that the energy U for a system of n electron is given by 3 by 5. This is U, energy. Okay, n times Fermi energy, EF. The electron at 0 Kelvin do not have zero energy because according to Pauli's exclusion principle, only one electron can occupy the zero energy level. All other electrons will occupy higher energy levels and will not therefore have zero energy. So out of these n electrons, only one will be in the zero energy level with zero energy. Others will be in other higher energy levels, the diagram that I drew just now. So each of them will have different energies, isn't it? So only the one at zero energy level will have zero energy. Others will have energies corresponding to the level up to the Fermi energy EF. So electrons at 0 degrees energy will not have 0 Kelvin. So now we'll prove this one, that U is equal to 3/5 of UF. Okay? Alright, let's stop.